Welcome to my online course in linear algebra for undergraduate mathematics. Today's topic of discussion is quotient space. First is definition of quotient of a subspace. If W be a subspace of a vector space V and A belongs to V, then quotient of W in V is defined as W plus A is equal to W plus A, where W belongs to capital W. Next is definition of quotient space. Let W be a subspace of a vector space V over the field F, and V by W is a collection of all elements of the form W plus A, where A belongs to V. Then we define two operations in V by W as follows. Vector addition is given by W plus A plus W plus B is equal to W plus A plus B, and scalar multiplications alpha W plus A is equal to W plus alpha A, where AB belongs to V and alpha belongs to F. Under these two operation, that is vector addition and scalar multiplication, V by W is a vector space over the field F. This vector space is known as quotient space. Next is proof. First, we shall show that the operation of vector addition and scalar multiplication are well defined in V by W, for which we consider two pair W plus A is equal to W plus B, W plus C is equal to W plus D. Then by using the property of quotient, that is, if H is a subgroup of G and X belongs to G, such that H plus X is equal to H implies X belongs to H. Generalize this property of quotient in group to quotient in vector space. We will get W plus A is equal to W plus B implies A minus B belongs to W, and W plus C equal to W plus D implies C minus D belongs to W. As W is closed under vector addition, therefore A minus B plus C minus D belongs to W. Rearranging the term, you will get A plus C minus B plus D belongs to W. As W is a quotient, by using W is a quotient in V, uh, by using the property of quotient, we will get W plus A plus C is equal to W plus B plus C, which shows that vector addition is well defined. That is, we consider two where W plus A is equal to W plus B and W plus C is equal to W plus D. Then after calculation, we have seen that left hand side, vector addition of left hand side is equal to vector addition of right hand side. Therefore, operation of vector addition in V by W is well defined. Next, we are going to show that scalar multiplication in V by W is well defined, for which we consider W plus A is equal to W plus B by using property of quotient. A minus B belongs to W. For any scalar alpha, we have alpha A minus B belongs to W. Then using the properties of vector space, as alpha belongs to F and AB belongs to B, so alpha A minus alpha B belongs to W. Again, using the property of quotient, I will get W plus alpha A equal to W plus alpha B. Therefore, scalar multiplication is well defined. That is, we consider the pair W plus A is equal to W plus B. For any scalar, we will get here W plus alpha A equal to W plus alpha B. You can also consider in the next step alpha W plus A equal to alpha W plus B. Therefore, scalar multiplication in P by W is well defined. Next, we consider AB belongs to V. As V is closed under vector addition, this implies A plus B belongs to V, and alpha belongs to F, A belongs to V. V is closed under scalar multiplication, so alpha A belongs to V. Therefore, W plus A plus B belongs to V by W, and W plus alpha A belongs to V by W. Therefore, V by W is closed with respect to vector addition and scalar multiplication as defined above. Next, we will going to show V by W plus is an additive abelian group. For that, first we are going to show B by W is commutative, for which we consider two elements W plus A, W plus B belongs to V by W, where AB belongs to V. Then W plus A plus W plus B is equal to, by using vector addition in V by W, it is equal to W plus A plus B. As AB are element of V and B is a vector space, B is commutative, so this can be written as W plus B plus A. Again, using the vector addition definition in V by W, we will get this W plus B plus W plus A. Therefore, B by W is commutative. Next is associativity. Consider any three element W plus A, W plus B, W plus C in P by W, where A, B, C are in P. Then check out what is the value of W plus A plus within bracket W plus B, W plus C, which can be written as W plus A plus W plus B plus C by using the property of vector addition in P by W. Then in next step, again using the property of vector addition in the V by W, I can write W plus A plus B plus C within bracket B plus C. This is from the vector addition property in P by W, which is equal to W plus A plus B within bracket A plus B plus C, as B is commutative. So in next step, again using the definition of vector addition in V by W, we can write W plus A plus B plus W plus C. Again using the scale vector addition, we can write this as W plus A plus W plus B bracket close plus W plus C. Therefore, V by W is associative. Next, since 0 belongs to V, then W plus 0 belongs to V by W. For any W plus A in V by W, where A belongs to V, check out what is the sum of W plus 0 plus W plus A. The sum of W plus 0 plus W plus A is equal to my W plus 0 plus A, which is equal to W plus A. Again, this can be written as W plus A plus 0. So this is equal to W plus A plus W plus 0. Therefore, W plus 0 acts as an additive identity of V by W. Next is inverse. W plus, for any W plus A belongs to V by W, where A belongs to V, then minus A belongs to V, as V inverse, additive inverse of its element in V is in V, and accordingly W plus minus A belongs to V by W. Therefore, W plus A plus W plus minus A is equal to W plus A plus minus A, that is equal to W plus 0, that is my W. That is, this is equal to W. Now, by using commutativity of V by W, I can write this one. Therefore, W minus A acts as an additive inverse of W plus A. Hence, V by W plus is an additive abelian group. Next, we are going to check out the remaining four property for a subset to be a vector space. For that, we consider two elements W plus A, W plus B belongs to V by W, and alpha beta belongs to F. Now, alpha W plus A plus W plus B is equal to alpha W plus AB by using the vector addition in V by W. Then in next step, we can write this as W plus alpha within bracket A plus B by using scalar multiplication property. Next, this this can be written as W plus alpha A plus alpha B, by as alpha belongs to F and AB are element of P. So and P is a vector space. Using the definition of vector space, I can write this as this form: W plus alpha A plus alpha B. Then again using vector addition, there will be one more step here: W plus alpha A plus W plus alpha B. In next step, we can use the scalar multiplication in P by W, and we can write this alpha W plus A plus alpha W plus B. Next, alpha plus beta, W plus A can be written as W plus alpha plus beta within bracket, and then A. In the next step, we can write this W plus alpha A plus beta A using the definition of vector space B, then W plus alpha A plus W plus beta A. Then again using the scalar multiplication property, I can write this alpha W plus A plus beta W plus A. Third condition, alpha beta within bracket alpha beta into W plus A, that can be written as W plus alpha beta A by using the scalar multiplication property in P by W. Then in next step we can write W plus alpha within bracket beta A, since alpha beta are element of F and A belongs to V. By using the definition of vector space, we get this one W plus alpha within bracket beta A. Then in next step, using the scalar multiplication property, I can write this alpha W plus beta A. Then again I will take this beta outside. By using the definition of scalar multiplication in P by W, I can write this alpha within bracket beta into W plus A. Fourth condition, 1 into W plus A is equal to W plus 1A by using scalar multiplication, as 1 is the unity of F. This can be written as W plus A. 1 into A is A. So this is equal to W plus A. Therefore, V by W is my vector space over the field F, and this vector space is known as quotient space. Next is a theorem. If W is a subspace of a finite dimensional vector space over the field F, then time of P by W is equal to time of P minus time of W. Proof. Since W is a subspace of finite dimensional vector space B, W is also finite dimensional. Let B equal to W1, W2 up to Wn be a basis of W. As W is finite dimensional, it has a finite basis. Let B equal to W1, W2 up to Wn be a basis of W. As it is a basis, it is linearly independent, and linear span of B is equal to W. And W is a subspace of P, so B is a linearly independent subset of B. By extension theorem, this linearly independent set can be extended to form a basis of B. So consider Vtex equal to W1, W2 Wn P1, P2 Pm be a basis of P. Then dimension of P will be the number of elements in Vtex, that is 1, 2 up to n plus 1, 2 up to m, that is n plus m. So dimension of V is n plus m. Again dimension of W is 1, 2 up to n. So dimension of W is n. Now dimension of V minus dimension of W is n plus m minus n, that is m. We will done if we show dimension of P by W is again m. For that we consider a set as consisting of m elements W plus B1, W plus B2 W plus Bm. We shall show that S is a basis of P by W. To show S is a basis, we have to show S is linearly independent, as well as the linear span of S is equal to P by W. First, we are going to show S is linearly independent. For that, we consider a scalar alpha 1, alpha 2 alpha m, such that linear combination of scalars with the element of S is 0. 0 of V by W, that is W. That is alpha 1 W plus B1 plus alpha 2 W plus B2 plus alpha m W plus Bm is equal to W. In next step, using scalar multiplication property, we will get W plus alpha 1 B1 plus W alpha 2 B2 plus W alpha m Bm is equal to W. This implies by using the vector addition property of V by W, we will get W plus alpha 1 B1 plus alpha m Bm is equal to W. This implies by using property of coset, we will get this element belongs to W. That is alpha 1 B1 plus alpha m Bm belongs to W. As B is a basis of W, so there exists scalars beta 1, beta 2 beta m, such that linear combination of these scalars with the element of B with the element of B, that is W1, W2, dot Wn will be my this element. That is alpha 1 B1 plus dot alpha m Bm is equal to beta 1 W1 dot beta n Bn. Beta n Wn. Bring the right hand side to left hand side. Bring this right hand side to left hand side. We will get this value. The vector v1, v2 up to vm, w1, w2 up to wn are the element of this set bdex, and bdex is the basis of b. That means bdex is linearly independent, so this scalar are 0. We have considered linear combinations of these scalars with this element are 0. We get these scalars are 0. That means our set S is linearly independent. That is, we consider linear combination of scalars and the vectors of S is 0. Then finally, after calculation, we get the scalar are 0. That means our set is linearly independent. Next, we will going to show that linear span of S is equal to P by W. Since linear span is a subspace of a vector space, so linear span is trivially a subset of B by W. Next, we are going to show B by W is a subset of linear span for which we consider any element W plus V in B by W, where V belongs to V. As Bdex is the basis of V, so there exist scalars alpha 1, alpha 2, dot alpha n, beta 1, beta 2, dot beta m, such that linear combination of this element B can be expressed uniquely as linear combination of these scalars and the vectors of Bdex. This vector of Bdex. As given this. That is B is equal to alpha 1 W1 dot alpha n W1 plus beta 1 B1 dot beta n Bm. Therefore, W plus B is given by W. Now put the value of B equal to this one, that is alpha 1 W1 dot alpha n Wn plus beta 1 B1 dot beta m Bm. The next step I will take up to this term, that is W plus alpha 1 W1 dot alpha n Wn plus beta 1 B1 plus dot beta m Bm. As W1, W2, Wn are the basis of W, are the element in the basis of W. Therefore, in place of this, I can write this is equal to W plus remaining element beta 1, B1 plus beta 2, B2 plus dot beta m, Bm. In the next step, you can write W plus beta 1, B1 plus W plus beta 2, B2 plus dot plus W plus beta m Bm. This is by vector addition property in B by W. Next, using the scalar multiplication property, I can write beta 1 into W plus B1 dot beta m W plus Bm. This belongs to, that means this element belongs to linear span of S. Therefore, B by W is a subset of linear span of S. That is, we consider any element in B by W, we will get this element in linear span of S. So B by W is a subset of linear span of S. Hence, linear span of S is B by W. That is, linear span is equal to the vector space B by W. That is, S is a basis of B by W. The number of element in S is the dimension of P by W. Here the number of element is 1, 2 up to m. So dimension of P by W is m. That is, time of P by W is equal to time of P minus time of W. Next example, if time of P by W is equal to 8 and time of W is 3, then find out time of P. We know that time of P by W is equal to time of P minus time of W, given time of P by W is equal to 8 and time of W is equal to 3. Therefore, from this equation, Dime of W can be written, dime of P is written as time of P by W plus time of W. Putting the value of time of P by W and time of W, we get 8 plus 3 equal to 11. That is the answer. Next is home assignment. Today I am giving you slightly different home assignment that I usually give you in my last lectures. That is, collect 3 to 5 years previous year question paper and check which question are solved in the class and which question are not solved in the class. The question that are not solved in the class, you should try to solve these questions. In case of any problem, doubt, difficulty, you should inform me. I will solve that question for you. With this, our 2 units are completed. Next Thursday, I will give you a doubt clearing session in unit 2. You should come to the department uh, between 12 to 12:45 p.m. I will give a doubt clearing class. You should clear your doubt, and remaining units are in my next lectures. With this, I would like to conclude. Thank you.